Good morning, dear students. Welcome back to physics class. Today, I am going to discuss on some related numerical of the chapter Mechanical Properties of Fluids. Let's see the questions. Question number 1 is, a metal block of area 0.10 meter square is connected to a 0.010 kilogram mass via a string that passes over an ideal pulley, considered massless and frictionless as in figure. A liquid with a film thickness of 0.30 millimeter is placed between the block and the table. When released, the block moves to the right with a constant speed of 0.085 meter per second. Find the coefficient of viscosity of the liquid. The metal block moves to the right because of the tension produced in the string. The tension T is equal in magnitude to the weight of the suspended mass M. Then, the shear force F is equal to T is equal to M into G is equal to 0.010 kilogram into 9.8 meter per second square is equal to 9.8 into 10 the power of minus 2 Newton. What is shear stress on the fluid? It is F by A is equal to 9.8 into 10 the power of minus 2 Newton by 0.10 meter square. You know that stress is force per unit area. Here, area A is equal to 0.10 meter square. Then, strain rate is equal to V by L is equal to 0.085 meter per second divided by 0.030 into 10 the power of minus 3 meter, where velocity of the block V is equal to 0.085 meter per second and the thickness of the film L is equal to 0.30 millimeter is equal to 0.30 into 10 the power of minus 3 meter. We know that coefficient of viscosity eta is equal to stress by strain rate. By substituting the values for stress and strain rate, we get eta is equal to 3.45 into 10 the power of minus 3 pascals second. Second question is, calculate the terminal velocity in air of an oil drop of radius 2 into 10 the power of minus 5 meter from the following data. G is equal to 9.8 meter per second square. Coefficient of viscosity of air is equal to 1.8 into 10 the power of minus 5 pascals second. Density of oil is equal to 900 kilogram per meter cube. The upthrust of air may be neglected. Solution is, given that radius of the oil drop R is equal to 2 into 10 the power of minus 5 meter, acceleration due to gravity G is equal to 9.8 meter per second square, viscosity of the fluid eta is equal to 1.8 into 10 the power of minus 5 pascals second, density rho is equal to 900 kilogram per meter cube. According to Stokes' law, the viscous force acted on the oil drop F is equal to 6 pi eta RV. If the velocity of the oil drop V is equal to the terminal velocity Vt, then the weight of the oil drop is equal to the viscous force, or weight of the oil drop is balanced by the viscous force, as there is only one opposite force acted against the gravitational force, or weight of the oil drop is the viscous force, because the upthrust of the air acted against the gravitational force is neglected. Then 6 pi eta r Vt is equal to m into g is equal to 4 by 3 pi r cube into rho into g. By simplifying, the terminal velocity Vt is equal to 2 r square g rho divided by 9 eta. By substituting the values of r, g, rho and eta, we get the terminal velocity Vt is equal to 0.0436 meter per second is equal to 4.36 centimeter per second. Third question is, the lower end of a capillary tube of diameter 2 millimeter is dipped 8 centimeter below the surface of water in a beaker. What is the pressure required in the tube in order to blow a hemispherical bubble at its end in water? The surface tension of water at temperature of the experiment is 7.30 into 10 the power of minus 2 Newton per meter. 1 atmospheric pressure is equal to 1.01 into 10 the power of 5 pascals. Density of water is equal to 1000 kilogram per meter cube. Acceleration due to gravity g is equal to 9.80 meter per second square. Also calculate the SS pressure. Let's see the solution. We know that the SS pressure in a bubble of gas in a liquid is equal to 2S by R, where S be the surface tension of liquid gas in the phase. Here there is only one liquid surface. For a bubble of liquid in a gas, there are two liquid surfaces. Then the required formula is 4S by R. Let R be the radius of the bubble. Now the pressure outside the bubble PO is equal to atmospheric pressure plus the pressure due to 8.0 centimeter of water column. So PO is equal to 1.01 into 10 the power of 5 pascals plus 0.08 meter into 1000 kilogram per meter cube into 9.8 meter per second square is equal to 1.01784 into 10 the power of 5 pascals. Therefore, pressure inside the bubble is Pi is equal to PO plus 2S by R. By substituting the values of PO, S and R, we get Pi is equal to 1.02 into 10 the power of 5 pascals, where the radius of the bubble is taken to be equal to the radius of the capillary tube, since the bubble is hemispherical. Fourth question is, figure A shows a thin liquid film supporting a small weight is equal to 4.5 into 10 the power of minus 2 Newton. What is the weight supported by a film of the same liquid at the same temperature in figure B and C? Explain your answer physically. See the solution. Consider the first case. Corresponding figure is A. Given that length of the liquid film supported by the weight L is equal to 40 centimeter is equal to 0.4 meter. The weight supported by the film W is equal to 4.5 into 10 the power of minus 2 Newton. Since the liquid film has two free surfaces, then the surface tension S is equal to W by 2L. It is equal to 4.5 into 10 the power of minus 2 Newton divided by 2 into 0.4 meter is equal to 5.625 into 10 the power of minus 2 Newton per meter. You see that in all the three figures, the liquid used is the same and temperature is also same for each case. Hence, the surface tension in figure B and in figure C is the same as in figure A, that is 5.625 into 10 the power of minus 2 Newton per meter. As the length of the film in all the cases is same, it is 0.4 meter, then the weight supported in each case is also equal to 4.5 into 10 the power of minus 2 Newton. And fifth question is, what is the SS pressure inside a bubble of soap solution of radius 5.00 millimeter, given that the surface tension of soap solution at the temperature 20 degrees Celsius is 2.50 into 10 the power of minus 2 Newton per meter. If an air bubble of the same dimension were formed at depth of 40 centimeter inside a container containing the soap solution of relative density 1.20, what would be the pressure inside the bubble? Solution is, given that radius of the soap bubble R is equal to 5 millimeter is equal to 5 into 10 the power of minus 3 meter. Surface tension of the soap solution S is equal to 2.50 into 10 the power of minus 2 Newton per meter. Relative density of the soap solution is equal to 1.20 and density of the soap solution rho is equal to 1.2 into 10 the power of 3 kilogram per meter cube. Air bubble formed at a depth h is equal to 40 centimeter is equal to 0.4 meter and radius of the air bubble r is equal to 5 millimeter is equal to 5 into 10 the power of minus 3 meter. We know that 1 atmospheric pressure is equal to 1.01 into 10 the power of 5 pascals. What is the value of acceleration due to gravity? It is 9.8 meter per second square. Hence, the SS pressure inside the soap bubble is given by the relation P is equal to 4S by R. By substituting the values of S and R, we get P is equal to 20 pascals. Therefore, the SS pressure inside the soap bubble is 20 pascals. The SS pressure inside the air bubble is given by the relation P dash is equal to 2S by R. By substituting the values of S and R, we get P dash is equal to 10 pascals. So, the SS pressure inside the air bubble is equal to 10 pascals. Then, at a depth of 0.4 meter, the total pressure inside the air bubble is equal to atmospheric pressure plus H rho g plus P dash. By substituting these all values, we get the total pressure inside the bubble is equal to 1.06 into 10 the power of 5 pascals. So, the pressure inside the air bubble is 1.06 into 10 the power of 5 pascals. Dear students, today's homework questions are given in this slide. Please, you have to work out these question answers by today itself. Okay, thank you. Have a nice day.